All right, anyways, let's get going with this. So what we are doing is this. You are going down to 2.1 statics. And then we are going to get to beam deflection, which is 2.1.2. Okay. So here's the beam deflection. Now, we're not doing this lab today. Now, this lab is actually something we would do in class. And it's fun. It's you stand on a beam, you watch Mr. Sputnik stand on a beam, and you all hope that I fall off and hurt myself. But obviously, we can't do that today. We're going to plan to do the lab. There's a distance learning version of this that we will be doing, which isn't too bad. And it'll be very similar. But today is just to learn the math and the calculations that will go into this. Okay. This is stuff that is really talking about like a structural engineer. Somebody's building a house. What is the type of joists I can use in my floors? And I would tell you that, it's funny. I remember when I had to do the training for this class, however many years ago, I then was walking by construction sites looking where they're building houses, and I'd see the joists. Okay. And if you don't know what a joist is a joist would be boards that are going to be spread a certain distance apart to hold up a floor. And all of a sudden I'm like, oh, that's why they do that. Okay, that makes sense. And to be honest, there's a lot of things. Obviously, you want to build something, you want to build it strong, but what do you think is going to be another really big factor? Strength, and when you build something, and being a structural engineer is going to be important. Okay, type in, don't hit enter. What do you think another really important thing an engineer is going to have to keep in mind when designing to build something? Think of something that you think is probably really important to any engineer, okay, when building something. And I want to see what you think, if you think what I think. All right. What is probably what? So we said strength, and you're like, obviously, hey, I want this board. I need to have so much that it won't bend and all that stuff, and it needs to hold this much weight. What's another really, really important thing that a structural engineer is going to have keep in mind when designing what kind of boards to use? Go ahead and put it in. Hit enter. Okay. All right. I know this is a really leading question too, so I know I'm or not, maybe not leading, maybe a little open and vague, and I'm doing that for a reason. Okay, so I see some good stuff coming up. I see angle, measurements, durability. Ooh, durability is really good, right? Efficiency, absolutely. Efficiency, actually, I would say efficiency, Christian, is pretty darn close to what I'm trying to say. Angle, measurements, durability. Gravity, yeah, gravity is always going to be there though. So gravity doesn't change, right? Location, I see some location, and that would be certainly for people buying the house, right? Location, 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 which is why I saw location a lot. Strength, yeah, strength I think would be the same. Size of stuff, location, cost. Ooh, I see it. I see it. And actually, I know other people kind of said the same thing. Money, 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 money. So that's why when you see these, I would start seeing these beams, and it's like, why are they using that beam? And it would turn out that you could take one beam that's going to be, you could get one beam that's super expensive. And, if you think about, ever see like exposed beams in like a log cabin or something, a nice solid beam. Well, it's not like you'd see those if you pulled up your floorboards, right? You would see beams that are much different and really are going to be basically like maybe not particle board, but chip board. And it'll be like not a full solid piece of wood, and then some other pieces, which we're going to learn about today. And the big thing, right? Yes, we need strength, but we need money. We need cost. We need to worry about cost. So when I see people say, and I'm going to assume efficiency, well, efficiency, I guess, could be like heat and stuff like that too. But yeah, cost is a big one. Okay. So that is something that an engineer, physicists would build something and just have pure forces. I'm a physics teacher, so I know, right? Physicists are doing everything ideal. The engineer is going to be the one that say, okay, well, we don't have $1 billion to build this doghouse, so we probably need to use, this type of material. Okay. All right. So let's get this party started here, and I'm going to go to. So you are looking at notes. So everyone sees where we're going. We're going to activity 2.1.2 beam deflection. Okay. You'll actually be doing the distance learning. Don't click on it, but you're doing the distance learning next class. But we will use the structural member properties tab. Okay. And here is our lecture. Is this way working okay for everybody to if I present this material this way? I don't have it preload or pre-recorded. Thank you for your input. Okay. All right. So there are two big terms you're going to need to know. The first one is going to be area moment of inertia, which we'll sometimes just call moment of inertia. All right. And then down below, we're going to have another one called modulus of elasticity. Okay. So what we're talking about today is what makes an object bend. So if I walked across these two beams, okay, what are the different ways what are the different factors that would go into making something bend? If I'm going to put if I'm going to use one of these beams to build the second floor of a house, how much will it bend? Will it be strong enough to hold me up? Okay, so this is really important stuff. We're going to do some number crunching, but understand that you won't have to stress out too much. Okay, the formulas will be ugly, but it's not like there's crazy algebra going in. Okay, all right. So that's what we're going to do. So the first thing we're talking about is moment of inertia. And here's the deal. I want you to look at those two beams. If those were the exact same beams. Now, here's where I'm going to say something. Does anybody know the actual dimensions of, okay, hopefully, does everybody know what a 2x4 is? Yeah, probably. Okay. Does anybody know the actual dimensions, what a 2x4 is? If you were to measure it with a ruler, what would you have? Come on, you guys need to be engineers, so you need to know this. Got one response? Well done, John Keene. Yes. Okay, so a 2x4 is really a 1.5 by a 3.5. And I will tell you that I would not know that in high school. Okay, I didn't really know that until I started building decks, the back of my house and all that stuff. So a 2x4, they actually subtract a 1/2 inch from it. So a 2x4 is really going to be a 2x4 piece of wood, okay, right, that you use to build things, is really going to be 1.5 instead of 2. All right, well, that'd be that way. All right, 1.5 by 3.5. So they actually subtract 1/2 inches. Now you do not need to know that for your calculations for doing like a test. You would need to know that if you were going to build something, okay. But I just wanted to share that info with you. All right. So, anyways, if let's say these really don't look like 2x4s, maybe I don't know, 2x6 or something like that. But let's say we had these two planks, and actually, I'm pretty sure if I scroll down, it'll tell me what numbers they want me to use. Oh, look at that. Hey, it was 2x6. Okay. Which way, if you had to walk across this plank or joist, and I wanted to walk across it, which way do you think would be the sturdiest, as in not bend? Chat me up. Very good, right? Yeah. So A is going to be the sturdiest. It's not going to bend. Okay. We're just going to know the numbers and the reasons behind it now. You already knew it. You already had, probably most of you could just feel it and say, oh, it'll be this way. We're just going to use the words and the terms and the math to go with it now. Okay. So the reason a joist is used for the floors as opposed to a plank, and if they're the same exact thing, is that a joist is going to be more sturdy. It's not going to bend as much. If we had it as a plank, when you walk the plank, right, that will bend a whole lot more. And it's literally the same exact piece of wood. It's just turning it on its side. Okay. And now all of a sudden it's strong. What we need to do first is understand how to calculate the moment of inertia. And here it is right there. There is our calculation for the moment of inertia. All right, now this letter XX is just going to say the point along this line. So if you draw an imaginary line, you're looking at a cross section. Okay, remember we already did this with centroids, right? We did the cross section. Okay, now we're going to do this as well. We're going to look at the cross section of this beam and figure out what the moment of inertia is. Okay, so these Douglas fir is a type of wood. They both are the same type of wood. They're really just it's orientation as in plank joist. Okay, they have the same dimensions. They have the same area, but one will have a much different moment of inertia. And it's because we have to use this equation right here. So everybody write down that equation. IXX, and that just means about what point, okay? And it would be from this point to that point, you know, the symmetry or whatever. Okay, is equal to base times height cubed divided by 12.
Mr. Spudik, where is this thing in
Go to my PLTW.
Yeah, I'm in there.
Then you go to your POE 2 point. If you go to 2.1 statics.
Yeah.
And then you go to sorry, I clicked off, but that's okay. I will get back to it. Then you're going to go to beam deflection, 2.1.2 beam deflection. And then you're going to go down to the structural member properties. Okay?
Okay.
All right, ladies and gentlemen. So this is what I want you to do. I would like you to do your calculations. Now, notice how we are given the width and the height, which is really going to be base and height, which is, you know, maybe they should have done base and height, considering we had an equation for base and height. I would like you to calculate the moment of inertia for beam A and beam B. They're the same one, but the joist versus the plank. Everybody do it now. Calculate on your calculators the moments of inertia between the two of them. Go ahead. All right, how's that? Are we good? Do we get our calculations? Do we need more time? Somebody tell me in the chat if you need more time. Okay. All right. So let's look at beam A versus beam B. Doing our calculation here. Okay, so beam A, our base in this case is 1.5 inches, where our height is 5.5 inches. Okay, the height's going to be, so the 5.5 is what gets cubed. And we get 21 inches to the fourth. Okay, 21 inches to the fourth. What about the other way? 5.5 is the one that's not cubed. The 1.5 is cubed. And we get 1.5 inches to the fourth. So I'm not saying that's exactly going to be lined in with what we're about to do, or at least not yet. I'm not saying it, but look at that difference in, you know, if you want to consider it strength. Okay, if this has something to do with strength. 21 versus 1.5. That's a huge difference, and it's because it's cubed. Okay, the cube value carries way more weight, figuratively and literally, okay, in this occasion. All right, so beam A is 14, so the joist is 14 times stronger or stiffer than beam B. Okay, all right, now check these out. Here's three options we got. All right, we got three options to build a joist with, and I'm going to tell you that this one here, if you say, Mr. Spudik, this is stupid, this is exactly what joists look like. The one in the middle of most people or most floors for, if you walk by, and please, If you are near any houses, if you're near a construction site, be careful and don't go into the construction site. But if you walk by a place where there's houses still being built, you'll see these. Okay, you will see exactly like this. Basically, you have a 2x4 on top, a 2x4 on bottom, and this middle piece right here is going to be chipboard or particle board going down the middle. And notice this is very, very thin. Okay. All right. So what I would like you to do is this. Wait, not yet. So we want to get the area for the cross sections. Okay. So I would like you to get using your equation up here, and we're already giving you the middle one. Okay. So I want you to do the moment of inertia using that equation right here for beams A for the one on the far left and the one on the far right. Okay, so calculate the moments of inertia of the two on the ends so we can compare it to what we got in the middle.
Mr. Spudik, I have a question.
Yes, man, Roop.
So so like when you get the inertia for two shapes, do you just like subtract them and see how big of a difference it is?
Well, I'm saying when you, so are you talking about up above when you're comparing these two?
Yeah, like these two, like
So notice all we did for these. So moment of inertia tells you it says it's going to be part of how it's stiff an object is. Okay. So a higher moment of inertia is going to be a higher stiffness, but they just divided them there, right? So they did 21 divided by 1.5 to see how many times stiffer it is. Not really subtraction. Now talking about shapes, we're not doing, you're not gonna have to worry about how to actually calculate the moment of inertia for this guy right here right now.
So like in this unit, we have to see like how many times it is, not by subtraction.
Yeah. In general, that's where normally when you want to compare two things.
Okay.
Okay. All right. So what I want everybody to do is calculate the moment of inertia for this. What is that going to be? It's not a 3 by 4.5, whatever. 2.5 inches by 4 inches. Calculate that moment of inertia. Calculate the moment of inertia of the 2.5 by 9.5. Okay. And we're telling you right away, the area of the middle one is 10 inches and the moment of inertia is 130. Okay. Okay. So go ahead and do that and take a few more minutes to get those calculations in. All righty. So did we get our calculations? We'll do the check your work, right? So checking our work. So area, all three of them have the same area. No, I'm sorry. They don't all three of them have the same area. The one block has a much bigger area. Okay. But if you think about the area between this one here, right? The far left, that little 2x4 or whatever, and the 2.5 by 4, and the middle one, that has the same area. Okay. So if you want to think about weight, right? So shipping and all that stuff, those would have the same, maybe not, I'm sure there wouldn't be the same price because of, however else you want to do it. But weight obviously goes into a lot about shipping. Those would be probably the same cost with weight, kind of, just at least with the weight part of things, the left and the center. Okay. Now the area of the other one, that other beam is definitely bigger, which means more weight, more cost. Okay. Now, moment of inertia, that 2.5 by 4 inch, you get a moment of inertia of 13.3. Okay. Is that what you got for your calculation? Give me a thumbs up if you got that. Good. Okay. All right. Well done, Francis. All right. I'll take the clap too. That's cool. All right. So then you go to the next one, and the middle one has a ridiculously higher amount of moment of inertia. What do we got? That's almost, I won't do the calculation, but that's almost 10 times higher moment of inertia for the same amount of area, for the same amount of weight, right? Now, then you go to the full beam. So if you had a beam that was a pure full wood beam that was 2.5 by 9.5, you would have a higher moment of inertia than the middle one. But for what cost, right? It's going to be, it's going to be more expensive to get those beams. A solid wood beam like that is going to be way harder to get, way more expensive to get than this little composite beam that you have in the middle there. So that's engineering, right? Because yeah, absolutely. If you want to get that big expensive beam, we're already saying it's going to be stronger. But is that worth the much higher price than the composite beam? And you can obviously tell the answer is no, because if you walk by any construction site. Okay. So that is the idea with these beams. And then obviously if you think about metal beams and all that stuff too, you're going to have that same T shape, right? Same idea, okay, when you're going with steel. Okay? All right. Does everybody see this and understand this with what we're doing for moment of inertia? We're almost done with moment of inertia here. Anyone have any questions about it? No? Okay, good. All right, here we go. Now let's talk modulus of elasticity. So now we compare two shapes that are the same but different materials. Okay? The modulus of elasticity is going to be a ridiculously high number, and it talks about the stiffness of an object when talking about the actual material. Okay? So we have two things here. We have Douglas fir and we have ABS plastic. And again, Douglas fir is a tree. Okay, Douglas fir is the wood you're going to get from a tree. Okay, and look at the difference of the modulus of elasticity. And now PSI, if we don't know what PSI stands for, that's pounds per square inch. Have we seen PSI with anything else?
Tires.
Exactly, with tires. So what are the PSI tires telling us? Pressure. Okay. So when we deal with PSI, we're actually talking about pressure. So tires, it would be air pressure. So you pump up your tires, that's important. You got to figure out, if it says, up to this max. I've seen, I remember having like a baby stroller and we over pumped one of the tires, or maybe it wasn't me. Maybe it was my sister-in-law, because I'd be way too responsible for something like that. But over pumping a tire, and then putting that tire putting the stroller in a car on a hot summer day and it exploding. Okay, PSI is pretty important. For everybody out there, if you ever look at a car, if you need to check your tires, if let's say your mom says, hey, go check the tire pressure, you always look at whatever the tire pressure says on the door. So you always just open up the driver's side door and you're going to see the PSI, pounds per square inch, on that door. Okay. Sometimes the values will be the same for front and rear. Sometimes the values are different. For my truck, I have different PSI values for the front tires as opposed to the rear tires with a truck bed. Okay. All right. So PSI is pressure. That's a pretty important thing to know. The PSI here, it's still going to be, it's still just telling you how much pressure and all that stuff with it. You don't need to look into it too much about it, but just look at the values. So which do you think is going to bend more? Is ABS plastic going to bend more, or is a Douglas fir if they're don't worry about anything more than the type of material. What would bend more? A wood from a Douglas fir, or wood from a tree, or ABS plastic? Chat me. Go ahead and chat me.
I'd say ABS plastic.
Exactly right. So plastic is going to bend more than wood. So now let's look at these numbers here. Okay. And I know I'm not sharing my screen anymore, but hopefully you have your screen up. Look at the modulus of elasticity for Douglas fir versus plastic. Okay. So we see the two of them. The modulus of elasticity for Douglas fir is 1.8 million PSI. The modulus of elasticity for the plastic is 410,000 or 419,000. Okay, so everybody try to understand this. Does a higher modulus of elasticity, is that higher value going to be how strong it is and show how much less it's going to bend? Or is that higher ABS or that higher modulus of elasticity going to tell you that it's going to be weaker and bend a lot more? And I know that wording was terrible, so don't try answering that with my terrible wording. Okay. But you just conceptualize. Okay. You think about those numbers. And if you see a really high modulus of elasticity, or you see two numbers and one has a bigger modulus of elasticity, you know it's stronger and you know that it won't bend as much. Okay. All right. So that's what you need to learn from modulus of elasticity. And now here is the big calculation. And here's what we're talking about. All right, so we've got to the point where we're actually going to figure out beam deflection. And beam deflection just means how much is the beam going to bend. So far, so good? So let's find a piece of paper here. So if we have a piece of paper and we want to see how much is going to bend, okay, there are going to be a few things that are going to tell us how much it's going to bend. So let's say I'm going to have something like that, right, sitting across there. And I'm going to put, I don't know if I have anything light enough. All right, I got that. So looking at that formula, everybody see the beam deflection formula? I'll share my screen again. And just give me a shout out if I forget again. Thank you, Manroop. All right. So looking at that beam deflection formula, here it is, okay? Do not be intimidated by this. Triangle means the change in, okay? So triangle means the change in. If anyone taken chemistry, you know that delta, right? Delta, the change in. So this is just telling you what's the maximum bend. Okay, so what's the maximum it's going to bend for any kind of material when you stand on it? And we have a bunch of numbers. It'll be okay. All right. The first one here is F for force. So if we want to know how much is going to bend on this paper, if I have something that's yeah. Whoa, there you go. Look. So that's a lot of force because this weighs a lot. So that would be a higher F for force as opposed to the USB. That's going to be a lot less force. Okay, so that's the first thing we have is force. So the amount of force that's going to be pushed down on it. The next thing is length, and length is pretty important. So look at, going back to this here. If I have, the length is the distance between these 2 points. Now I'm going to explain why there's a triangle here and a circle there. Okay, a pin and a roller. We'll talk about that some other time. But understand this, the length we're talking about for the distance is going to be how far apart, here, where do we think it's going to be stronger? Is it going to be stronger like that? Is it going to bend less here? Or is it going to bend less like that? Or, right? Am I asking that right? So if you have the length is pretty important. If we're talking about the two supports, how those two supports are going to hold, if it's close up together here, that's going to be a whole lot stronger. It won't bend as much. I move these further apart, I'm going to get more of a bend. All right, so we've already analyzed, so we know What the symbol means, delta max means how much how much it's going to bend, how much further down it bends than if nothing was sitting on it. We have F for force, how much weight will be on the beam, okay? And we have L, which is cubed in here, and that's the length between the two supports. All right? Okay, then we have the number 48. And if you think that's random, I don't know how they got this equation, but I can guarantee it has something to do with calculus and having to bring a number down below from a derivative, or either derivative or integral. All right. And if you don't know what I just said right then, don't worry about it. All right. Then we have E, and we already figured out what E stood for. E was the modulus of elasticity. These numbers. So if I'm doing this calculation for bend or for deformation or deflection, and I wanted to talk about this being a Douglas fir, I would be using 18 or 1.8 million. And if I was doing plastic, this number here would be the 419,000. Okay, still pretty big numbers. All right. And then we have the I right here, and the I is just going to be our moment of inertia that we just calculated up above. Okay. All right, ladies and gentlemen, I am almost done talking here. And I apologize if this isn't one where you can't fast forward me. I'm guessing now you realize that fast forwarding is a whole lot easier than having a recording. Okay. So looking at this, here we go. Let's go through the steps on this on the site. So here's the equation. This is showing the object, right? And the equation in here. Okay. So if we use Douglas fir and we had 200 pounds of force, 250 pounds of force, all right, which is not me. Okay. But we had 250 pounds of force. We had a heavy weight on there. The length of the wood was 96 inches. All right, so an 8-foot piece of wood. All right, we have the Douglas fir, the 1.8 million psi, and we have the 20.8, which would be apparently whatever moment of inertia we calculated there. Okay, that means if the wood looked that way and you stood on it, from sitting flat against the supports to somebody stepping on it, it would bend in the deepest part in the center. It would bend down 0.12 inches. And that'd be something where you could actually just hold a measuring tape up. You know, here, let's say here's the beam. You know, you measure it when nobody's standing on the beam. And then you get the person that weighs 250 pounds and measure it again. And it would have gone down 0.12 inches. Okay. All right. So then we go here. Try to calculate. So how about this? That is a calculation we did for the Douglas fir. All right. Using the same length, moment of inertia. Okay. You're given 2. All right. That's where we got the moment of inertia. Go ahead and calculate the delta max. So I'm gonna mute myself. Everybody do that calculation. Try it out and see what you get for the calculation for the max deflection of the plastic. Go for it. And I'm going to stop sharing. All right. So let's share. I'm going to share a screen, go over it. And obviously you have the same thing. So do the calculation for the ABS plastic. We will get 0.53 inches. So a little over a half an inch, it will bend. So plastic would be pretty expensive anyways, right? But plastic is going to bend a whole lot more. So it's not like you're going to build a joist with a half inch of or with that plastic, because bending a half inch every single time would probably not be the way you want to deal with carpeting or hardwood floors or any of that stuff when putting something down. Okay, so I want you to understand this. There's going to be slight calculations. Do you need to memorize this formula? Heck no. Okay, do you need to memorize any 3 of these formulas, right? You got moment of inertia, you got modulus of modulus of elasticity is not really a formula. But you need to, elasticity and beam deflection. You don't need to memorize the two equations, okay? But I want you to understand what is going on, what we're talking about, okay? When you're building something as an engineer, it really is kind of important whether or not something's going to bend, okay? Bend is better than breaking, but it's not great. All right, so this is what you're going to do, ladies and gentlemen. You are going to do this little review, okay? And I've created a very easy basic assignment just to say, yep, I did what I was supposed to do and paid attention, all that stuff. And that will be in your assignments here. So if you go